All right, well, it looks like the recording has started, so welcome everyone and hello. This is Rebecca Dallin with the City of Oklahoma City Stormwater Quality and the Central Oklahoma Stormwater Alliance, or COSWA. I would like to officially welcome everyone to this special training event. If anyone is interested in receiving a certificate of attendance for this training, please send me an email to request it. I will need your email address to be able to send that certificate to you, so please don't request those in chat. If you have any questions about the certificates or haven't received one within a couple of days of the webinar, feel free to email me. And I'm going to put my email address into chat right now so everyone will have that handy. Please be sure to keep yourselves muted during this presentation. If you have any questions, simply type them into chat. We will have time at the end of each presentation for questions. Today, we'll be hearing from several University of Oklahoma and Oklahoma State University graduate students who will be presenting information on their stormwater-related research projects. Up first will be Brittany Moehnke. Brittany graduated from Oklahoma Christian University with a Bachelor of Science in Chemistry. She is completing her master's degree in geology at the University of Oklahoma and will begin pursuing a PhD there next semester under the guidance of Dr. Caitlin Hodges. Brittany is a member of Critical Zone Biogeochemistry Lab Group and is interested in sediment transport and soil chemistry, including organic carbon and heavy metal storage across different redox and moisture conditions. Next, we will hear from Yaseen Alwazzan. Yaseen is an international student from Kuwait. He obtained a bachelor's degree in environmental engineering and is working on his master's in environmental engineering. Yaseen has worked for the Oklahoma Water Survey for over 3 years, during which he analyzed data, collected field samples, and worked as a lab technician. His hobbies include baking and painting. Very interesting. Our third presenter will be Mengting Chen. Mengting Chen started her PhD program at Oklahoma State University in August of 2018. She is investigating the effect of climate change on water erosion under the supervision of Dr. Jamie Schussler. And finally, we'll be hearing from Mahyar Taheri. Mahyar is currently a graduate research assistant pursuing a doctoral degree in civil and environmental engineering at Oklahoma State University under the supervision of Dr. Jamie Schussler. His research focuses on flood detection and risk assessment through satellite imagery and hydrological modeling. Originally from Iran, Mahyar earned his Master of Science in Civil Engineering with a specialization in geotechnics from Karzami University in Tehran. Beyond academia, he is a certified swimming trainer and has experience as a lifeguard. I'm going to stop sharing the welcome screen, and Brittany, if you'll go ahead and start sharing your presentation, you can take it away.
All right, thank you. All right. Can you all see my window? My screen?
Yes, we can see it. Very
Excellent. Good. Okay. Well, thank you for having me. As you all just heard, I'll be sharing research I conducted over evaluating suspended sediment loads in a watershed in Oklahoma. This was actually part of my master's thesis work, and I did this project under the guidance of my advisor, Dr. Hodges, and Dr. Jason Vogel, one of my committee members, actually recommended me for this talk, so I'd like to thank him for that. But with that, I'll go ahead and get started and share what I have for you all today. There we go. So, as you all likely know, erosion and suspended sediment can detrimentally impact water quality. Specifically in Oklahoma, this has been a problem historically with events like our Dust Bowl in the 1930s causing drought, which dried out our soils, and following that, we experienced flooding that caused a lot of runoff into streams and creeks around here, and this was due to poor farming practices that prevented the retainment of soil on farms, but in modern times, even though we've taken measures to improve our regenerative agricultural practices and such, we still do struggle with water quality in terms of nutrient loading and suspended sediment. Specifically in Lake Thunderbird, we've had experiences in high sediment load and nutrient loading, and Lake Thunderbird is a source of drinking water for Norman residents. And my research focuses specifically on a subwatershed within the Lake Thunderbird watershed, which is Dave Blue Creek, um, depicted in that orange square there. It was identified in 2016 by the City of Norman's Compliance and Monitoring Plan to establish best management practices for poor water quality in Lake Thunderbird as a problem area. Kind of, as you can see, it's depicted in that red-ish region. And despite this monitoring plan being in place for about a decade, as of 2023, it was still failing to meet acceptable levels of total dissolved solids and had high suspended sediment content. And this was attributed to likely poor responses in terms of identifying the sources of the suspended sediment upstream, as well as increasing development in this area. Oh, sorry. And to investigate this, I started looking at sediment fingerprinting, which is a way of creating a composite identifiable signature using geochemical techniques. This can be looking at the mineralogy of the soil or sediment that's loading into a creek. It can be looking at isotopic tracers like nitrogen isotopes from plants, or it could be heavy metals, nutrients, rare earth elements. I used more metals and rare earth elements due to the similar nature of the soils that could be loading into my study site. But that decision, like I said, is kind of based off of the study scale and your source groups you're looking at to identify potential areas of sediment loading in our watershed. I actually use the National Land Cover database to identify different source groups based off of their land use. I divided these in between developed regions, which are depicted along the kind of teal color dots on that portion of the tributary to Dave Blue Creek. And we have the blue, which represented our tree cover sites, and pink, which represents our grassland areas within this subwatershed. I then constructed a suspended sediment trap, which is essentially this big PVC with a sort of cylindrical opening that's pointed toward the direction of flow so that you can capture the small suspended sediment within the stream and empty it after a period of time, which is what makes it a passive sediment trap. And that's just a picture of my advisor and I deploying the trap for the first time. Here it is within Dave Blue Creek. Oh, sorry, meant to explain this. So after we deployed our trap around the same time, we collected soil samples at those sites that I identified based off of land use. That's what those individual points were. I meant to point that out. And we collected those both as surface scrapes from the tops of the soil as well as along the bank profiles so that we could maybe differentiate between surface runoff and bank erosion. And with those samples, we ended up inputting them into our source tracing unmixing model that I'll talk about in a bit. I also wanted to talk about the stream conditions over the sampling period. On my black bar here, it's just showing our mean daily value discharge at Lower Dave Blue Creek, which is where my sediment trap was, and then our pinks are gauge height. The black lines there represent each of my sampling dates. I collected my suspended sediment from the trap I deployed once a month so that I could get an adequate volume of suspended sediment for geochemical analysis over each period. And one thing you'll kind of note is we had much higher discharge in over the first couple months of the experiment, and rather low towards the end, which this lasted from September through November. As I kind of alluded to, I did some geochemical analysis to identify those sediment source fingerprints. And these samples were analyzed for whole rock geochemistry using an aqua regia digestion by an outside laboratory. But I took these element concentrations and put them into the sediment source assessment tool, which is an unmixing model. And it identifies different source group fingerprints, and it weighs select tracers by their predictive power, which essentially means it will identify which identifiable group that could be a source. So like I said, I did tree cover, grassland, and developed areas as what percent it contributes to the overall sediment load within your system. And this model is also great because it includes some robust air analyses, like a Monte Carlo simulation, and identifying your source group accuracy as well. The results of my mixing model showed that the majority of our suspended sediment over all 3 months was from our developed areas. Here it's marked as urban. And within the first 2 months, we also saw high inputs from the grass-covered areas. Within November, which was our month with our lower stream discharge, as well as actually less precipitation as well, we did see a forest tree cover signature as well. And looking into this a little deeper, we did that air analysis I kind of alluded to as well, where we're looking at individual samples and running them as if they were an unknown sample and seeing if they're fit appropriately into their correct source group to kind of determine whether or not our fingerprints we used accurately identify a sample as belonging to its source group. And we did find that there's a bit of a confusion matrix in differentiating between our bank and our upland samples for the same source categories, which is why you'll see in my previous slide that we ended up grouping by land use alone rather than bank versus surface erosion. However, you'll note that we did see pretty decent agreement within our developed bank samples, which is depicted on the bottom there with mainly the blue, which kind of indicates that our developed bank samples are very different than the surface erosion occurring in developed areas. Oops, it's not. Sorry, my screen just froze. There we go. The other air analysis that we did was that Monte Carlo assessment, and it found those just basically run your model over several iterations, removing random samples, and it found really good agreement between each one, so we don't have any samples that are necessarily skewing our results. And yeah, when we only looked at samples by land use alone rather than bank versus surface erosion, we had that good agreement. Oh, I keep freezing. Okay, there we go. And the one thing about the model is we use it to identify fingerprints that we can use in the future to identify these land uses, which is what led us to our eventual percent contributions. And these tracers are supposed to be conservative tracers, which would mean that they can't be altered in concentration significantly between your sources of the sediment, so our soil erosion, and downstream where it's captured. so that you can use their percent abundances to evaluate and associate it with the different sources. And we found that arsenic, magnesium, um, niobium, scandium, all those were our most reliable source tracers and led to our most accurate geochemical fingerprints for each land use group. Um, One thing that was also notable was that our suspended sediment, although within the range of making these tracers conservative, was higher in a lot of our samples um, of our suspended sediment relative to upstream within the soil, which could have some implications for buildup of metals and rare earth elements within our system as you get downstream, which is something to consider. But overall, our most notable finding was that throughout all those 3 months, we did see the developed samples have a signature in our suspended sediment. And this could have impacts for anthropogenic activity that could be seen in higher concentrations of the trace metals and the rare earth elements that we identified. And you'll also note that I mentioned the developed bank source group was different in its signature than our developed surface areas. And this could imply that we need to focus on retention strategies on bank areas within developing portions of the Dave Blue Creek watershed rather than surface runoff in those areas. The other point that was kind of considerable was that the shift from grassland to tree cover contributions that we saw matched the decrease in our discharge and actually corresponded with precipitation events over those 3-month periods. So this could imply that our grassland signatures could be due to runoff in areas without a good riparian zone, as opposed to that tree cover signature could be a more localized input that is almost your baseline when there isn't a lot of precipitation events or flooding happening. And yeah, with that, future erosion mitigation strategies in Lake Thunderbird watershed could focus more on those bank stabilities in those developed areas and looking at evaluating runoff in grassland areas. Um, and yeah, that's all I have for you all today. I forgot to input my source slides, but if you have any questions or need to kind of clarify significance of my findings, please take it away.
Great. Well, thank you, Brittany. Looks like we do have a couple of questions popping in.
Oh, perfect.
First of all, some kudos. Derek says, great presentation and thank you for the information. His first question is, how did you determine a target depth to sample suspended solids? And then he does have another part of that. He says, for clarification, was the sampler developed to acquire a single crab sample or composite sample?
Okay, yeah, those are excellent questions. So for the first one, how did I determine the target depth to sample my suspended solids? Um, Mainly through literature review, we just ensured that our trap within our creek was kept at below our surface level of our water, but high enough that it wasn't really getting any kick up from the bank floor. For our soil samples from the upstream sites that we used as our tracers, we did surface scrapes of the soil and vertical transects of the banks, which kind of goes into the next question. Yeah, we used the sampler to acquire composite samples over those month-long periods, mainly to get an adequate sample size because if you notice that the time of year that I conducted this project was from August through November. We weren't having a whole lot of precipitation or very high discharge other than that event in the first month. So we kind of needed a whole month to get an adequate sample volume. It would be nice to do something that's more event-based as well.
So, Brittany, can you describe a little bit how the sampler works? Maybe go to the picture of it that you have.
Absolutely. Is my screen still sharing?
Yep.
Yeah, okay, perfect. Let me. Yes, so it's like I kind of mentioned, it's a cylindrical sampler that's on some posts that we put kind of just, I'd say probably, I think we determined like at 40% above our stream floor. And we have these small inlet tubes, which I didn't really mention my sample processing, but following the capturing of the suspended sediment within the stream, we sieves to a uniform grain size prior to analysis. But we have these small inlet tubes and an outlet tube to allow the flow of water, but it's at a small enough opening that it allows for the suspended sediment to enter, settle in the bottom of our sampler, and for the water to exit. Those dimensions are accurate to the one we have as well.
Cool.
Does that kind of clarify? Yes, thanks. Yeah, does anybody have any other questions or?
I would make note for everybody that Brittany is staying on for her PhD, at least as of a month ago, unless she's changed her mind since then, and is going to be continuing some of this research and going more in depth on some of the things that she saw in this kind of smaller proof of concept study. So stay tuned. In a couple of years, she might have some more stuff for you.
Yes, that's the plan.
Awesome. Well, thank you, Brittany. I don't see any more questions in chat, so if you will stop sharing your screen, we will invite Yaseen to share his screen.
Thank you.
Thank you, Brittany.
Let's see. Can everyone see the slides?
Yes, very good. Thank you.
Awesome. Okay, well, hi, my name is Yaseen, and today I'll be sending you my findings on revisiting the performance of a subsurface flow wetland for removal efficiencies for pyrethroids and nutrients from nursery runoff after 9 years. So a little background on this research. It is located in Oklahoma City in a retail nursery. And being in a nursery, the nursery workers have to monitor for imported fire ants, as it is classified by the USDA as an invasive pest for damaging agricultural crops such as corn and sorghum. To combat their spread, which is typically during transporting of nursery stocks and soil containers, they established a quarantine zone in the southeastern border of the U.S., and part of that quarantine zone is going over a portion of Oklahoma. And to prevent their spread, the USDA recommends using pesticides such as bifenthrin, fipronil, and chlorpyrifos in their soil containers when they're transporting these nursery stocks to or from these quarantine zones. The problem with this treatment solution is that when the nursery's containers reach those sites and they begin irrigating, these pesticides will begin to leach off these pots during runoff of irrigation and end up in storm drains, which is harmful for aquatic species. And the reason they are harmful is these pesticides are neurotoxins that affect the nervous system. And some of these pesticides that I mentioned are pyrethroids, organophosphates, and phenylpyrazoles, each of which has an aerobic half-life over 100 days. And bifenthrin pyrethroids has the highest partitioning coefficient, which adheres to organic substrates, whereas fipronil has the lowest coefficient, which is very low absorption to soils. Previous research has been conducted on this location, in which during 2016 they constructed a bioretention cell that acts as a subsurface flow wetland. For the purposes of this research, I am classifying it as a subsurface flow wetland because, unlike a bioretention cell, there is constant water in the system, whereas in a typical bioretention cell, the water drains between irrigation cycles. So they constructed it during the summer of 2016 and then began monitoring from the summer to the fall of the same year. Their two primary goals were the hydraulic performance of the system, as well as measuring the pesticides and nutrients removals. Looking towards the table to the right, our hydraulic performance found that the site is losing around 78% of the water that's entering the system during irrigation cycles and is infiltrating underground. Whereas their pesticides, they found it to be between 74 to 99% removals, whereas their nutrients were between 78 to 86. Now, it is important to note that fipronil had a negative 14 removal. That is because the concentration that was entering the system was the same concentration exiting the system. So the current goals for this research were similar to the previous researchers' goals, which is to monitor the hydraulic performance of the system after 9 years, as well as monitor the pesticides and nutrient removals. Here is an aerial view of the location of the system itself. The retail nursery is about 16 acres in size, but the system itself has a drainage area of about 0.55 acres. And it receives water from the field, which is highlighted in green, and as well as water from the greenhouse, highlighted in red. It is sloped towards the street, so the water would flow from the top of the screen towards the bottom. Here's a bit more description on the site. The construction of the subsurface wetland has a concrete wall surrounding the perimeter of the site, but the bed is exposed to subsurface soils. The water would enter from the forebay, which is about 5 by 5 by 6 feet in dimensions, where 6 feet is the depth. Connecting the forebay to the cell are 9 3-inch PVC pipes. The cell itself is about 29 feet long and is comprised of 1.5 feet of river rock. Above the river rock is 4 feet of concrete sand, and separating the medias is a geotextile between the sand and the river rock, and another geotextile liner is between the river rock and the subsurface flow soils. The water exits the system via underground infiltration, as well as 2 upturned underdrains, one of which has a standpipe, as well as an overflow at the top with 0.5 feet of ponding. For irrigation, during warm temperatures, the nursery would irrigate on a daily basis. And sometimes when the temperature reaches triple digits, they would irrigate twice a day. However, when the temperature is below 75 degrees, and then they would irrigate every other day, being Mondays, Wednesdays, Fridays, and Sundays, which was the time that they were irrigating during this research. They also irrigate around 35 minutes per section. So they would begin at the field before transitioning over to the greenhouse. The main source of this irrigation is groundwater wells. And things that were worth mentioning before we began this research was that during the summer of 2023, the nursery had to remove and replace 3 feet of soil from the cell due to the fact there was an overgrowth of cattails that needed to be removed. And when inspecting the forebay, there was a considerable amount of sediments and algae at the forebay, which likely caused some of the pipes to be clogged. So when we set up the site, the first thing we have done was to dig a trench towards the storm drain. So as I mentioned, the water flows from the greenhouse towards the streets. And so this trench was dug to allow the water to enter the storm drain during overflow. To prevent the water from the field irrigation to enter the cells from the side, we used a 2x6 wooden barriers with a silicone and gray stuff foam sealant to fill up the gaps and prevent water from entering or exiting the system where it's not intended. We also built a berm at the inlets to channelize the water from the greenhouse towards the forebay. So the greenhouse water enters through a corrugated pipe towards the forebay. And during the previous researchers' research that he did not install a berm at the inlet. We also had to coordinate with city officials to access the storm drain to install any of our under drain flow measurements. We also had two metal boxes, one located at the forebay and the other located towards the overflow, where we house our sampling instruments. For our sampling instruments, we used to monitor flow, a variety of flumes, such as a 0.5 flume at the forebay, H flume at the forebay. For the underdrain, we used a Palmer bolus flume. As I mentioned, there was two underdrain pipes from the system. And so to record the data, we have sealed one of those pipes to have the water exiting from the other pipe. For the overflow, we used a 60-degree trapezoidal flume. To collect the water that we were sampling, we used 3 Teledyne ISCO Blizzard auto samplers with refrigerators. They collect samples into 14 of 950 milliliter bottles in a rosette with an arm distributor. And per bottle, they would deposit around 750 to 800 milliliters before transferring on to the next bottle. And the waters were collected using a Teflon lined tube. To collect the data, we used a ISCO Bubbler Module 730 at the forebay and overflow auto samplers to record the flow, and used a Solence level logger and barrel logger at the underdrains stilling well for the level logger, as well as 2 more level loggers at the forebay and the cell to measure the hydraulics. The samples that were collected were composited within 24 hours from collection, and they were refrigerated at all times until we began compositing, from which we composited based on flow of each event. And when we composited, we used a Teflon churn splitter. And so when we collected the bottles and measured the weights, depending on the volume that we received, we would use either a 14 liter or an 8 liter accordingly. In the events that the water that we've collected was less than 3 liters for the 8 liter churn, we use a glass jug with slow rotation to prevent bubbles from forming. And this was typically done at the overflow. The samples that were composited were sent for analysis for nutrients to OSU's Soil, Water, and Forage Analytical Lab for Ortho-P and Nitrate N. For pesticides, we used the University of Nebraska-Lincoln's Water Science Laboratory for a comprehensive pesticide scan. We also done some water quality parameters that were done in-house for pH, turbidity, and specific conductivity. Now we're going over to our hydraulics results. So this is the graph for the inlet. The y-axis showcases the flow in gallons per minute, whereas the x-axis is the duration of each irrigation event. And so the blue line represents the winter from which we researched in the winter of 2024, whereas the red lines are during the previous researchers' summer 2016. And as we can see, there's significantly more water entering the cell during the winter compared to the summer due to the fact that we've used a berm at the inlet to channelize all the greenhouse water into the forebay. And that gave us an average peak flow of about 21 GPMs compared in the summer without the berm, which gave us between 6 to 7 GPMs. We also, hold on, it froze a bit. All right, so we also done some underdrain hydrographs to give you a broad spectrum of the amount of water exiting the system. The underdrain averaged around 2.5 GPMs during the winter, and it was very low during the summers due to the fact that there was less water entering the system, hence there was less water exiting the system. When it froze again. All right. When we monitored for the forebay and the cell hydraulics, the graph on the left is showcasing the winter irrigation, which occurred every other day. And the graph to the right is during the spring of the 2025, where they occurred on a daily basis. And as we can see, the difference between them is during the winter, where they irrigate every other day. The water level significantly falls down to about 4 feet before being recharged from irrigation events. Whereas in the spring, the water maintains a much higher depth, which in turn has a higher volume in the system. And so this results in a higher head, which results in a higher infiltration. So this is seen in this infiltration graph that we've done in inches per day. And so our infiltration was measured over a duration of 7 hours after the water have reached below the underdrain discharge point. to ensure accuracy. And so as we can see during the winter, when they're irrigating every other day, the infiltration rates at the cell and the forebay were much lower compared to infiltrations occurring during the spring when they occurred daily. Something of interest is during the summer of 2016, the forebay has a wide range of infiltration values. That is because over time, over the course of 2 months, the infiltration rate began to decrease as a result of fine particles settling at the cell. Now going on to our water quality results that we received from our labs. For our nutrients concentrations, we have done so in our graphs using our x-axis for concentrations in milligrams per liter. For our inlet, this represents the forebay concentration, whereas the outlets are representative to the underdrain and overflow. And as we can see on the left, the ortho P is following the one-to-one trend line, which shows well removals while irrigations occur. However, when we look to the graph on the right, our nitrate N, there is considerably more concentrations exiting the system compared to what is entering. Comparative mass balance by using our hydraulics and the concentrations, we found that about 99% of the water is infiltrating subsurfacely, as well as our nutrients and nitrates are also have a 99% reduction due to the fact of the infiltration. The water was very turbid, was very clear with low turbidities. However, during overflow, the turbidity increased due to the sediments being picked up by the water at the surface. It is important to note that what was interesting is the pH of the groundwater increased and became more basic, as well as the conductivity decreasing between 2016 and 2024. So what does it all mean? Well, adding a berm at the inlet increased the inflow to the cell, which allows more water to be captured by the system and be treated. But it also meant that a lot of that water that was treated is infiltrating. So in the 2016, it was infiltrating about 78% of the water entering, whereas now there is 99% infiltration, and that is likely due to the berm adding more water to the system rather than being bypassed. This also meant the increase in volume also resulted in infiltrations increase. However, it was less infiltration in 2024 rather than in 2016. This is likely to the sediment buildup I've mentioned, as well as the increased irrigation frequency also resulted in increased frequency of infiltration due to the increased head. In terms of water quality, the pH of the well has become more basic compared to 2016. This is likely results to the groundwater itself have increased in pH, and that the water turbidity is decreasing at the underdrain, but is increasing at the overflow. But there's still 99% removals, and it's less than 1% exiting the system in terms of water. Because we have 99% removals for water, we also have 99% removals for mass of nutrients due to high infiltrations. And although the nitrate concentration is increasing, it is still 99% from infiltration. We're still waiting on our pesticide data from the University of Nebraska. And some observations was that since the forebay had a lot of algae and sediment, that likely needs to be cleaned, as I believe that the lower rows of connection pipes are clogged. We also believe that further research could be used to document the insecticides found at the forebay, and that adding a berm at the inlet increased the fraction of water entering the cell, and therefore increasing the percent of removal rates that's preventing it from entering to the storm drains. And the site has a good layer of smishsteka, which is an organic matter that helps pesticides to be adhered to it when it has a high KOC coefficient. It has been removed during the summer of 2023 when the cattails were removed by the nurseries, but it has built up well. And overall, over the past 9 years, the cell has been performing well. It's preventing nutrients from entering the storm drain. Yes. So I'd like to acknowledge a couple of people, such as Dr. Vogel and Dr. Zamor, for helping me, guiding me through this process of this research, as well as John Bullock for helping fabricate the H flume. I'd also like to thank Dr. John McMain for sharing his raw data and 2016's research as the previous researcher, and most importantly, the Oklahoma Water Survey undergraduates for helping me with the field and lab work. Questions?
Okay, we do have a couple of questions popping in. One from Nathan. Did you use synthetics, pyrethroids, or were natural pyrethins used as well? If both, were there any variations in your findings? If only synthetics, do you hypothesize if a difference if natural pyrethroids were used instead? And then, of course, he says, thank you and good job.
So we didn't apply any of these pyrethroids into the system. It is something that the nursery itself applies and treats for, and these are running off from the containers that they're receiving.
So usually it's bifenthrin is by far the most common, and that's what we're mostly seeing in these, although there's similar levels of other things. But we actually haven't got the pesticide results back from the lab at the University of Nebraska yet, so we can't necessarily talk a lot to what we're seeing yet right now.
Like, I believe the previous researchers' data concentrations, he showed that the pyrethrin was about 50 nanograms per liter. The aquatic benchmark for fish was about 40 nanograms per liter. And when the concentrations were collected from the underdrain, it was about 13 nanograms per liter. So there was the removals in 2016, but I won't be able to tell until I get the data for current.
Okay, cool. Derek has a couple of questions. Are you measuring for metabolic breakdown of those pesticides? Okay, go ahead.
No.
Okay, and then did you independently test the different stormwater control measure parts, such as the forebay and the sand filter?
Could
Or
you?
was it all just one unit?
I'm not sure I understand the question.
We're testing the whole system at once, basically, like what's coming in and what's going out. Because you can't necessarily test in the middle of the system the way that it's set up and get a mass balance per se.
And both Nathan and Derek, did that answer your question sufficiently, or we good there? Okay, cool. Thank you, Derek. Okay, good. Any other questions for Yaseen? All right. Well, I don't see any popping in, so thank you so much. Great presentation, exciting work.
Rebecca, could I add one additional comment?
Oh, yeah,
since we're losing 99% of the water to infiltration, my expectation is that, we're 98 or 99% pesticide removal as well, because I wouldn't think we'd be picking up, a magnitude or two in the little tiny bit of water that comes off. And so the fact that it works better hydraulically now than it used to, it's still not, there's hardly anything getting to the stormwater system.
Well, thank you for that. All right, and up next we have Mengting. Can you go ahead and share your screen? And don't forget to unmute.
My screen.
Go ahead and push start the slide presentation, because we're seeing the stuff on the left too.
They'll basically go about.
There you go. Yes,
Okay,
that's perfect.
Okay, it works. Okay. Thanks. Thanks for having me. I'm Mengting Chen. I'm going to present a study, a spatial temporal analysis of rainfall erosivity in Oklahoma. Rainfall erosivity is a parameter to predict water erosion. Water erosion is a process of detachment, transport, and deposition of soil particle because of action of water. So the water erosion has a wide range of impacts. It can change the shape of slope, leading landslide, which threaten to infrastructure and human safety. When rainfall splashed on the soil surface, it alters the soil's property, such as reduced surface soil permeability. As a result, less water infiltrates in the soil layer and more becomes surface runoff. This is particularly concerned in urban area, where increased runoff will heighten the risk of flash flooding. The runoff carries detached particle, especially the construction site runoff, which will lead to water quality degradation, disrupting aquatic ecosystem. Another major concern is the loss of topsoil, the most nutrient-rich layer of soil, directly impact crop yields and the long-term soil health, ultimately induce economical issues. Altogether, water erosion is destructive to human life, nature, environment, and social economics. To support the development and the implementation of soil and water conservation practice in agricultural, forest, and construction side, the universal soil loss equation and its revised versions, USO, Russell and Russell 2 were developed to measure water erosivity by predicting soil loss. Rainfall erosivity is one of parameter in the USO and the Russells. The rainfall erosivity measures the capacity of rainfall to affect water erosion. The rainfall erosivity is defined as a product of kinetic energy of a single stone, and it is a maximum precipitation amount within 30 minutes. So it is a value estimated using kinetic energy equation and rainfall intensity in a small time interval as input. The high value of rainfall erosivity indicates more intense rainfall events and a higher potential of water erosion. So rainfall erosivity, the rainfall kinetic energy equation is a regression equation. This table summarizes several commonly used equations and the spatial coverage they applied for and the erosion model they are integrated with. So, the ISO erosion map was generated to provide a local value of rainfall erosivity, serving as the input layer for localized soil loss estimation. This figure is the original ISO erosion map. This map was generated using rainfall gauge data recorded before 1960. After calculating the annual rainfall erosivity at each gauge site, the point of equal values were connected as line, so-called ISO erosion line. The value for the locations between the lines are obtained by linear interpolation. This is the most recent map of rainfall erosivity. After estimating monthly rainfall erosivity at the gauge site, the point-based data was interpolated to Russell map. However, the kinetic energy equation used to calculate erosivity for this map is applied for the region outside of the US. Since the rainfall erosivity is estimated from rainfall data, its value is tied to precipitation patterns. The precipitation characteristics are changing because of climate change, driven by the increased greenhouse gas emissions. Compared to last century, many eastern US are getting wetter. Some southwestern areas are becoming drier. In addition, the frequency of extreme precipitation events is increasing across the contiguous US. Zooming to Oklahoma State, when compared to the average annual precipitation over the 20th century, over past 30 years, 20 years experienced wetter years, while 10 years were drier than the average. We also can observe a shift in precipitation pattern from 2000 to 2015. Oklahoma experienced dry years. However, after 2015, there was an increase in both the frequency and the magnitude of wet years. Above all the discussion, the published maps contain some limitations. The rainfall data used to estimate rainfall erosivity is outdated, and they may not reflect current precipitation conditions, particularly on the ongoing climate change. The kinetic energy equation used to generate rainfall erosivity value may not well suited for some specific locations. Given those concerns, an update to rainfall erosivity is necessary. Therefore, the objective of this study is to update rainfall erosivity using modern precipitation data for the state of Oklahoma. In addition to support local soil and water conservation practice, the spatial and temporal variation of rainfall erosivity across Oklahoma is investigated. The research task of this study include data collection, pre-processing, erosivity computation, spatial and temporal analysis, and raster data generation, observing the difference between update and published map. This study collected 5 minute interval rainfall data from Oklahoma Mesonet. The historical records covering the period from 1994 to 2024. Two types of spatial delineation, NOVA climate division and the EPA level 3 ecoregions we used in this study to explore the spatial distribution of rainfall erosivity. Oklahoma is divided into 9 climate division and 12 ecoregions. The whole state exhibit diverse climate and ecological features. Before calculation, the missing data and the site, less than 10 years of records were removed, ensuring the rainfall data used in this study has a long-term and reliable historical records. The remaining 111 sites were used in the computation. The kinetic equation from Russell 2 was used to calculate rainfall erosivity, since this equation is applied for the region in the US. The spatial variation in average annual and monthly rainfall erosivity across gauge sites located within climate divisions and ecoregions was analyzed. We also observed the variation in the long-term average monthly erosivity within 1 year. This analysis is to measure how erosivity fluctuates from month to month and identify seasonal peaks in rainfall erosivity. The value of monthly erosivity at a gauge site were interpolated into 12 monthly raster map, then aggregated into an annual erosivity raster map. The published ISO erosion map reported in Agricultural Handbook number 703 was digitalized in raster layer, serving as a reference. The difference between the update and the published map was assessed using the relative percentage difference. Here, this page illustrates the monthly variation in rainfall erosivity across Oklahoma. The erosivity begins to increase in March, peaks in May, and remains a high value above 500 to October. This this pattern is also reflected in the monthly erosivity map on the right side. As for the spatial distribution of annual erosivity across the climate division and the equal regions, the northeast, central, and east central, southeast climate division had an annual value greater than 5,000. There are 8 equal regions had an annual erosivity greater than 6,000. The relative difference show the annual erosivity has increased across most part of Oklahoma. The maximum increase up to 112% occurs around the eastern mountainous regions. A few areas in the northwest part of the state show decrease in rainfall erosivity. Focus on the central region. The bar chart shows the monthly distribution of rainfall erosivity. January to March have relative low value. The increase started in April, with significant jumps in May. The peak occurs in June. July to October also remain high value of monthly erosivity. After October, erosivity declined by December. The high value spans from April to October. This temporal trend suggests that conservation practice should be in place by April and maintained through October to prevent the soil loss during the vulnerable months. The map on the right side shows the spatial variation. The central region has 12 counties and overlay within 3 EPA level 3 ecoregions. Each county has annual erosivity over 5,000. The counties of Creek, Oklahoma, Sanibel, and Oklahoma exceed 6,500 rainfall erosivity. This area may require more targeted conservation efforts due to their high potential to water erosion. Our next step is to move from monthly rainfall erosivity database towards a more granular database, ideally at the daily scale. This transition aims to improve the temporal resolution of rainfall erosivity database and better capture the interannual vulnerability in rainfall erosivity. It is crucial for more accurate soil loss estimation and erosion mitigations, especially when considering the cover management and the support practice, because they all change the soil surface seasonally. In addition, more robust erosivity estimation approach need to be developed. For example, integrated machine learning techniques could enable to estimate erosivity more effective and efficiently. In summary, this study calculates rainfall erosivity using modern precipitation data measured per 5-minute interval, ensuring the erosivity value reflect the current climate condition. This study also investigates spatial and seasonal variation of rainfall erosivity across Oklahoma. Based on annual erosivity, the central region has a higher potential for water erosion. The temporal variation in the central region is quite consistent with the temporal variation over the whole state. The high values occurs from April to October. Thanks for your attention. I'm happy to take any question you might have.
Sorry, I got too click happy on there. Thank you. That was a really interesting presentation. So, and this may be like a future phase of your project, but I'm wondering how those differences in erosivity affect watershed modeling and possibly best management practice efficiency. So I don't know if you can speak to that at all.
Sorry, can you repeat it?
Oh, sure. How did the erosivity differences affect watershed modeling? Or do they? They may not. I don't know. But
in fact, currently in this, the erosivity is integrated in the soil loss modeling in USO and Russell. This erosivity represents the rainfall splash for the water erosion because of rainfall splash. Maybe the high erosivity will the region has a high erosivity can predict the high runoff. So in this study, we only consider the USO and the Russell. As for the sediment estimation, in the USO and the Russell in this study cannot give this kind of result. Yeah, but high soil loss will yield high sediment result. Yeah.
Okay, cool. Any other questions for Mengting? I don't see anything in chat just now. All right, well, thank you for a great presentation. All right, you can go ahead and stop sharing if you would. And then Mahyar, go ahead and share your screen.
Yes. Can you see my
Yes.
presentation? Okay.
Yes, it's perfect. Thank you.
Yes. Hello, everybody. I am Mahyar Taheri. I am a PhD student in Oklahoma State University. Today, I'm going to talk about the flood risk mapping, integrating remote sensing, hand and hydrodynamic modeling. First of all, as a motivation of using remote sensing for flood mapping, you know that flood inundation modeling and risk assessment mapping is essential and vital for disaster preparedness and emergency response and infrastructure planning. As you see in the image at the top, on your right, you can see that there is a flood in 2019 in central part of Oklahoma, and because of this flood, many urban areas and also infrastructures such as bridges and roads are affected. In this study, we used a satellite which name is Sentinel-1, and it is SAR satellite. What does this mean? SAR stands for as a synthetic aperture radar. This satellite launched in 2014, and the SAR satellites are using microwave wavelength in order to imagery. You can see that the range of a microwave wavelength in the image at the top bottom of the screen. Also, this satellite use C-band for imagery. What does this mean? As a general information, the satellites use three types of bands: X-band, C-bands, and L-bands. X-band has the shortest wavelength and also the shallowest penetration, and it's used for airband mapping and tracking the land changes. Also, C-band has the moderate wavelength and penetration. It's used for flood mapping and detecting the water bodies. And after that, we have L-band in satellites. It has the longest wavelength and as well the deepest penetration, and it's used for the root zones detection. And the study area in this study located in Verdigris River near Inola in the eastern part of Oklahoma. And why I picked this study of area is that this area experienced a major flood in May 2019. As you see, based on the Mesonet precipitation map, this area experienced more than 14 inches of rainfall in a short period of time, about 10 days. And as you see in this image, it is Verdigris River in May 2019, and you can see that many lands in the vicinity and the neighborhood of this river affected by the flood. The method which we used for flood detection is creating temporal RGB images. What does RGB image means? These images consist of three types of pixels. R stands for red. It shows the urban area. G is green. It shows us the vegetation areas. And the B is blue. They are for water bodies, both permanent and temporal. In this method, you should have two types of image, pre-event and post-event. And by tracking the changes between these two images, you can find out about the changes during the time. As you see at the top of the slide, you can see the raw image from the Sentinel-1. And after processing and applying the method, you can see the RGB images. You can see in the post-event, we have some blue pixels, light blue pixels that I highlighted them with red circles. You cannot see these type of pixels in the pre-event images. So they can show us the temporal water bodies, and yes, they can be categorized as a flooded area. And after that, we used this, machine learning techniques for classification in order to extract our desired data, and also to extend the method from one image to more image. We used machine learning techniques. For better visualization and being more tangible, I tried to align and match the finding with real-time data. You can see this is a part of our study area, and before applying the method. And after applying the method, when there is no flooding in this area, you can see that the river as a water body completely detected by the method. And after that, after the flood happened, in the post-event image, you can see that many area in the vicinity of the river affected by flood, and our method can detect this flooded area. So, of course, we have some limitation in order to use this satellite, and it is the most important of them is the time temporal and the temporal resolution of satellites. Each satellite has a temporal resolution. It means that the time that line that's which satellite take picture from the same area. For Sentinel-1, it is 12-day as a time interval, and yes, actually we may miss some event between these two time intervals, and in order to remove this issue, we should go to the another satellite with a similar characteristics. As a result, for the flood detection by this method, you can see this chart. The y-axis in the left and show the water area with the orange bar, and in the y-axis in your right you can see the precipitation, and the right bottom and top x-axis show us the date range. I use the red baseline in order to show the initial total water detected by this method. And you should know that this is both temporary and permanent water. If you look at the time and the date at the about early April and early of May, there is no precipitation. So we can consider the water area which detected by method as a temporary, a permanent water bodies, such as lakes, river, and so on. But after that, if you look at the middle of the May, and the area experienced a high amount of precipitation, and you can see that the water area detected increased suddenly, abruptly. And yes, it can show us we had something such as flood happening in this time interval. And if you see the trend after that, by passing the time, the precipitation decreased, and the water body detected decreased too by our method. And yes, by tracking the deviation from this baseline, you can see the meaningful changes in water extent over the time. As second part, in order to preparing the flood risk map, we used the concept of flood depths in order to preparing flood risk maps. And for estimation, the flood depths, we use the popular method, which name is HAND. HAND stands for as a height above nearest drainage. And it says that when we have a flood, the depth of water at any point can be estimated by subtracting the elevation of the ground at the point from the elevation of the water surface in the nearest drainage. As you see, this method needs a DEM model, and DEM model show us the elevation and the altitude of each point in our map from the sea level. You can see the schematic image of hand method providing to better insight of this method, and in your right, and also a flow chart and algorithm in order to create hand result from the DEM model in your left. For our study area, you can see at first, at your left, we prepared a DEM model for the Tigris River in the east of Oklahoma. The legend of the map show us the elevation of each point based on the meter, and it is from the sea level. And after applying and leveraging the flowchart and creating hand model, you can see in your right the result of the hand. If you see in the value, you can see that this map tell us, for example, the dark green area, if our study area experienced a flood, the dark green area shows us the flood depths in that point. For example, if you go from the dark green to red and to yellow, and after that to the red, yes, the flood height can be decreased. In order to preparing the risk assessment map, the methodology is based on the first creating hand model, as you see, and after that creating synthetic rating curves. What is the synthetic rating curves? Synthetic rating curves used to estimate flood risk in the ungauge or data scarce location. In our study area, at first, we divided into multiple sub-regions, and for each sub-regions, we try to extract the historical and geometrical characteristics, as you see further, and after that, we tried to create risk assessment maps. We need three types of data for creating synthetic rating curves, and after that, risk assessments. Also, we use 5 locations in order to gather data. As you see in this picture, they are mentioned by the USGS ID numbers. The nearest is Inola, and after that you can see the other stations. And also I showed you for you the flow direction. So the study of area located on the downstream of these locations. And I picked up this location because in the downstreams our study area act as a reservoir, and it is more convenient and easy to detect water in these downstream reservoirs. Yes, and you can see the exact location of the study area. It is near Inola. So we use three types of data. The first one I got them from USGS, and they are hydrograph charts. You can see the discharge versus the time for the each locations. After that, I used NOAA data in order to get the flood data for each locations. You can see for each location the minor, moderate, and major height of flood in the time of May 2019, and also the existent probability of flood. And after that, in order to creating synthetic rating curves, I extracted the geometry of the streams in our study area. You can see that for each station, I gathered the width, slope, and the maximum peak flow based on the NOAA and the minor flood stage. And after that, I used Manning equation in order to creating rating curves. Also, as you know, each physical and hydrological model has uncertainty. In order to cover uncertainty, I used two types of N, coefficient of roughness in Manning equation. The Manning equation is so sensitive into these parameters. So in order to remove or decrease the impact of uncertainty which produced by this coefficient, I use two type of value for this coefficient. And as you see, the orange chart in the rating curves show the specific data for the flood events in each station, and the blue and the red and the green chart show the Manning result by different values of n coefficients. At the last part, I get the maximum peak of the flood for each stations, and as you see, by having them and using rating curves, I use the maximum discharge and try to evaluate and estimate the depths corresponding to the each maximum peak of flow. And as you see, for example, for this area that I showed you in our study area, I tried to generate these rating curves. As a summary, and by gathering the data, you can see these flood risk assessment maps. This flood risk assessment divided into three parts. The green area is the highest water level. It's the low chance to happen. As you see in the table above, in the green area, the flood depth estimated is 11 meter. So the chance of happening this type of flood is low. So it categorized as a low risk area. On the other hand, the red area flood depth estimation is about 3 meters. So it is high risk area. The probability of occurrence of this flood is high. And also we have a brown area. It's a transitional area that I categorize it as a high risk, and the flood depths needed in this area is 6 meters. This can be mentioned as a flood risk of our study area. In order to validation this map, I used modeling, HECRAS 2D modeling. I used input a hydrological graph for one of the station as a input for our modeling. And you can see that I use the DEM models and also the hydrological graph for our study area. And you can see the result of modeling in HECRAS. you can see that the flood extended on the 21st of the May 2019, and after that, by extending the flood, you can see that as I showed you in the legend, the flood depths in each point by extending the flood during the time. After matching the result of the HECRAS modeling with our risk assessment map, you can see that as I showed you in the image on your right, after matching the two outputs, you can see that the high risk area has compatibility about 67% with our risk assessment map. Low risk area compatibility is about 20%. And yes, actually we noticed about some error as area about 8%. The main takeaway of this risk assessment map based on the rating curves is that the flood depth estimation by hand model and HECRAS model showed us the good compatibility with approximately 1.5 kilometer from the river center line. If you imagine a center line of the river, by going far as a 1.5 kilometer from each side, we can see the best matching between our result with HECRAS and our risk assessment map. On the other hand, when we go further from the river, and yes, the compatibility between the two models decrease, and it shows that the limitation of each models in accurately capturing flood dynamic in area further from the river and streams. As a conclusion, and you can see that for the remote sensing for flood detection, satellite imagery is highly effective for mapping flood areas because it uses microwave length, and it is not vulnerable to cloud or any other block such as dust and other things. And however, a key limitation is that the remote sensing alone cannot provide flood depth estimation because only the surface can be observable by the satellite imagery. Also, the model which we used is widely used and so popular, and it's an efficient model to estimate flood depth using trained data. And the HECRAS model successfully captured the flood extent on the May 2019 with 67% of precise for predicting flood-prone area. And yes, that's all about our research, and thank you for your attention. Now I'm open to questions.
Great. Well, thank you. What a great presentation. I don't see any questions in chat. If anyone would like to unmute and ask any of our speakers a question, please feel free to do so. At this time, go ahead and stop sharing if you would. Yeah. All right. Jamie, Dr. Schussler, do you have anything to add today or to discuss?
Hi.
Sorry to put you on the spot.
No, that's okay. I don't have a lot. I'm sorry, I have weird backlight because of my window. I don't have anything necessarily to add to the presentations. The PhD students know the stuff inside and out. One thing I did want to mention, though, is that we are, so I guess I'm representing South Central International Erosion Control Association as well today. I'm on the board for that, and also the planning committee for the conference that will be held in Oklahoma City in October. And we are looking for abstracts for that. Since it is in Oklahoma City, we would love to see just local knowledge, local case studies, especially coming out of any MS4s. We want to try to fill out an MS4 track. And so just a reminder that the South Central region represents Oklahoma, Arkansas, Louisiana, and Texas. So it should pull a nice crowd. But it's always great when we can have that local support and local case studies. So I've shared that with Rebecca, and I think maybe we could get it in a newsletter or an email out to everybody. But if you have any questions, happy to chat on that.
Yep, we are working on getting that newsletter out. So I'm trying to pull up the conference website real quick so we can put that into chat.
Rebecca, can I advertise one thing too?
Yes, yes, you can.
So next Thursday morning at 9 o'clock, I teach an LID class in the spring and have 5 really strong groups that are pulling together some semester projects. And I had sent advertisements out to a few folks, but it will be via Zoom between 9 and 10:15 next Thursday. And so if you are interested in just logging on and listening to what the students are designing for their sites, there's 3 teams that are designing LID into McKinley Park in Oklahoma City, one team that's designing LID into the engineering quad here on the OU campus. And another team has kind of a different type of a project where they're creating 15 themed rain garden plant palettes for plants that work in Oklahoma. It's a class that's interdisciplinary between engineers and scientists and landscape architects and planners, including Yaseen and Mr. Joel Dixon, who is also on the call today. And used to work for the city of Newcastle. I think actually might still be a contractor for them. So anyway, if anybody's interested, we would love to have you on Zoom and ask some zinger questions for my students, challenge them a little bit.
Great, thank you. I think, okay, there we go. I did kind of put my blurb that's going to be in the next, gosh, I need to get that out soon. Next COSWA newsletter, I put that blurb into chat. I also got the call for abstracts flyer put into chat that Jamie had mentioned. So I think I've got a lot of the bases covered here. Oh, good. Thank you for posting that as well. So great. And of course, if anyone has any questions for our speakers, I think they're all still on as well. But I think we are ready to wrap up. So thank you all again for joining us. I'm going to go ahead and stop the recording.